Hello, and welcome to the first of a two-part webinar introducing you to the Wolfram language. My name is Nia, and I am a technical presenter with Wolfram Research, a technology company founded in 1987 by Stephen Wolfram. Our flagship product is Mathematica, a computational software program first released in 1988. For more than 28 years, we have continued adding new technologies to our portfolio of products. The core of all of these is the Wolfram language, a flexible and powerful high-level programming language with built-in algorithms and computational knowledge. In this series of webinars, we will be using Mathematica software to write programs in the Wolfram language. While there exist specialized software packages for individual areas, such as high-speed numerics or network analysis, we aim to have sophisticated functionality for a broad range of areas, developing over time. To give you an idea of what you can do with the Wolfram language, here are some examples of more developed tools. This is an interactive phase plot of a chaotic attractor. It has many interactive elements, as well as multiple dynamic graphical outputs. While the previous example was created to be highly customized, here is a tool that is inbuilt, with all of the formatting done for you. It is a financial trading chart with interactive elements and accurate curated data from the Wolfram knowledge base. There is a difference between Mathematica and the Wolfram language. Mathematica is the software which provides you with an interface with which to code in the Wolfram language. It has many useful tools which we will discuss more later. For now, we will talk about how the Wolfram language is written. To give you an idea of what the Wolfram language looks like, here is a piece of code. Don't worry about what the code means just yet, we will get into that soon. Some important attributes of the Wolfram language are that it is high level, so it tries to automate processes as much as possible. Multi-paradigm, meaning that you can code in many different styles. You might hear that a language is procedural or functional, but the Wolfram language mixes styles. Also, the functions are written in English, using full words. This can make it easier to understand what the function does at a glance. To get to the built-in documentation, go to Help, Wolfram Documentation, or press F1 while in a notebook on Windows, or Function F1 on a Mac. If there are any functions or areas of the Wolfram language you want to know about, then try searching or browsing the documentation. To try out the functionality of the Wolfram language, there are several free options. If you would like to use a desktop software, we provide a trial version of Mathematica available on our website here. If you want to use a browser and the internet, then you can use a free account of Mathematica Online here. For some of you, your place of education will hold a license for Mathematica, which means that you can use the full version for free. Talk to your head of department or IT services to find out more. Before we get started, there are a few requirements for this course. It is important that you try out the code as you learn, so make sure you have access to the Wolfram language. You don't need to be a programmer to learn the Wolfram language, but it is important that you know your way around a computer and how to use programs. And again, you don't need to be an expert, but the concepts of functions and variables are very useful when using Mathematica. This is the first of a two-part webinar teaching you the basics of the Wolfram language. This time we will be talking about an introduction to the basic syntax of the language, how to get the most out of a Mathematica notebook, starting to create your own programs with functions and variables, and dealing with data. Next time, we will look at how to visualize your output in different ways, how to make interactive applications, and finally, some mathematical and statistical functionality. When Mathematica is first opened, you are presented with a Welcome to Wolfram Mathematica screen that provides a list of your recently opened documents and links to resources designed to introduce you to Mathematica's powerful feature set, in addition to the options to create a new notebook, slideshow, or other Mathematica document. Documents in Mathematica are called notebooks with file extension .nb. Screen environments change how your notebook looks and behaves. You can access them from the menu here. There are four main environments: working, for continuous creation and coding; presentation, an expanded version for easier display to groups; printout, as your notebook would be printed on paper; and slideshow view, where you can view slides one at a time with a navigation bar across the top. For now, keep your notebook in working environment. Mathematica works by having code in cells. Each cell can be evaluated individually, and you can see the cells by hovering your mouse near the right of the notebook. You will see a series of brackets that show where each cell is. To write and evaluate a different piece of code, you will need to create a new cell. To do this, move your mouse below the existing cells until your cursor becomes horizontal or flat, rather than vertical or upright. You then click, and a grey bar should appear, meaning you can start writing to create a new cell. The grey bar that appears is called the cell insertion bar, and it indicates that you can start typing to create an input cell. An input cell is in input style, meaning that you are writing code. The style of a cell indicates how it will behave, how it looks, and how it is grouped. To style a cell, select its bracket, right-click, and go to Style. Alternatively, you can select the cell and go to Format and Style. You can see down the right there are keyboard shortcuts for doing this more quickly using your keyboard. Try making several cells of different styles. Once you have done that, you should see that the cell brackets are now layered. If you double-click the outer layer of a group, it should close. When it is closed, the visible cell bracket should have a small dark triangle to indicate that there are hidden cells underneath. To reopen, just double-click the outer cell bracket again. Now that you can create a notebook with different styles, let's start making some code. There are several tools that can help you in a notebook. First of all, there are toolsets called palettes that give you an easy point-and-click interface for entering characters and objects. Select the palettes item in the menu and select Basic Math Assistant. This provides a calculator, several basic mathematical functions and formatting, as well as access to symbol insertion buttons. Let's insert a sine function into a new cell. You can then fill in the slots and then press Shift-Enter to evaluate. Secondly, if you are struggling to find the name of a function or want some data from the Wolfram knowledge base, you have full access to Wolfram Alpha through Mathematica. Start a new input cell and type a single equals sign. This should turn into an orange square equal symbol. This means you can now type a query in natural language, and Wolfram's semantic interpretation will turn it into a structured query and return a result. Note that this requires an internet connection. Try to keep your query in simple words, then press Return to get a result. There are 3 points to notice about this. First, while the cell is evaluating, the cell bracket turns black. This also indicates that only one cell can evaluate at a time. Secondly, on the left-hand side, there are small pieces of writing. Your input cell says in brackets and a number. This number indicates the number input that you have made. So I have created 19 input cells, and then 19 output cells have been created as a result. So this is the matching output cell. Underneath the Wolfram Alpha query that you have just made, there is a line of code which can be clicked. When you do that, the alpha input is replaced with Wolfram Language code that does the same thing. This is a very useful tool if you don't know the proper command for a task, but can phrase it in simple words. In Mathematica 10, we provide a code assistant and suggestions to help you complete your function names and code more quickly. Start typing plot with a capital P in a new cell. When you type, you'll see a pop-up under your writing suggesting various function names. Either click on one or select it with the arrow keys and press Enter. This will complete the full name. Once you have completed the function name, you can press the down arrow or Command-Shift-K on Mac or Control-Shift-K on Windows. This will give you a pop-up of all the possible formats of that function. If you select one, it will be inserted with slots for each input, which you then can fill in and move through using the Tab key. There are options you can apply to many functions. Once you have finished entering the main arguments, you can add a comma, and then press Command-K or Control-K to see a list of possible options. When you select one, it will be completed and provide suggestions for possible values. Finally, the documentation is an in-depth resource that provides you with descriptions and examples of all the Wolfram Language functionality. You can get to the documentation through the Help menu, or you can click somewhere in a function you want to know more about and press F1 on PC or function F1 on Mac. The name of a function or command in the Wolfram language is an expression. The structure of an expression is this. There are three main parts to an expression. The head, which is its name, which is written in camel case. Each word has a capital letter. Square brackets that indicate where the arguments will go. Finally, arguments inside those square brackets, separated by commas. Whenever you write Wolfram Language code, the three key things to remember are capital letters for expression names, square brackets after that, and press Shift Return to evaluate code. A useful expression to remember is information or question mark. It is used on the head or the name of an expression to find out more about it. This is often a lot quicker than opening the documentation, but it can provide less information. Expressions often do not appear in their usual form in notebooks, with a head and square brackets and so on. For example, 1 plus 1. This is really shorthand for plus, square brackets, 1, comma, 1. We can find this structure using full form. Let's try it now. This will give the wrong result because of the way the Wolfram language evaluates. The inside of the brackets happens first, and then the outside. So 1 plus 1 will evaluate to 2, then full form will be used on that. To stop this, there is a function called hold. And now we can see the real structure of 1 plus 1. This example uses nested expressions, meaning using an expression as an argument to another expression. This can be done with lots of types of objects, including maths, pictures, lists, and so on. Normal expressions are expressions that can take other expressions as arguments and behave as you have seen so far. Atomic expressions are the building blocks of Mathematica. They are the smallest chunks of code that you will see. Some examples of atomic expressions are numbers, integers, rationals, reals, and complex numbers. Symbols, any group of characters not starting with a number. And strings, anything in double quotes, and usually coloured grey. Everything in Mathematica is an expression, and apart from some atoms, will have the structure head, square brackets, and arguments. In general, maths in Mathematica is done in the same way as other computer algebra systems, with these symbols indicating different operations. Take care with multiplication in Mathematica. Multiplication can be entered either with the asterisk operator or by placing factors next to one another. When you type a single space between two numbers, Mathematica will automatically convert that space to a multiplication symbol. If you write an expression with a number followed by a symbol, Mathematica will interpret this as multiplication. It is a good idea, however, to use explicit spaces to indicate multiplication. Note that two symbols written together must have an explicit space between them for the expression to be interpreted as multiplication. XY is a symbol containing two characters. X space Y is the product of two single-letter symbols. It is a good idea to explicitly write the asterisk so there can be no confusion. To make a variable equal to a value, you will use the expression set, the shorthand being an equal sign, written like this. Notice that when the variable was assigned a value, its colour changed. When it was blue, it does not have any value, and when it is black, it does. All symbols in the Wolfram system behave that way. Once you have used set and the variable has turned black, the Wolfram system will always insert the value of the symbol into computations. So in this case, x will be replaced with 2. You can use information or question mark on user-defined symbols to find out any assignments it has been given. If you wish to get rid of definitions for a symbol, use clear. Clear will remove all definitions for that symbol. It can be used on multiple symbols at once. Often, you want the output from a symbol to change each time you use it. When you use set, just an equals sign, the expression on the right-hand side is evaluated, and then the result is assigned to the symbol on the left. When you use set delayed, or colon equals, the whole expression is assigned to the symbol, and then when the symbol is used, it gets evaluated. With a constant value, such as 2, this makes little difference. However, if you want something such as a random number, it needs to change every time you evaluate it. If you use set here, random real will evaluate to 0.32 or some other real number. Then, whenever we use the symbol rand, it will be 0.32. However, when we use set delayed, colon equals, the output will change each time as the expression random real is assigned to rand1. No output is returned when the assignment is made. However, when the function or symbol is evaluated, a different value might be returned. This is necessary for several situations, most importantly when defining functions. Defining a function requires the use of blank, underscore, to indicate that values will vary from evaluation to evaluation. The form of the function should follow the same rules as built-in functions, with the exception that capitalization is not required. If you use a capital letter, then you can't tell the difference between user-defined functions and inbuilt functions. There are other methods to separate them, such as putting a letter or your name before the function name, but we will stick to the lowercase method here. Let's define a function here called fun. Don't forget to use square brackets, as this is an expression. Then here we're saying our input will be called x. Blank or underscore is written to indicate that this value will change each time. Then we use set delayed, as we want the right-hand side to vary as well as the input. Don't forget to evaluate your definition. The symbol fun has now turned from blue to black, so it has a definition and we can use it. There are several ways to tell when your function definition has gone wrong. Let's clear fun for now, so I can show you what happens when things aren't correct. If you forget to use colon equals, you can see that the right-hand side x's are no longer green. This means that that x does not refer to the input x we have defined here. It instead refers to the x that we defined earlier, which in this case is 2. Let's try defining that. You'll see now that you get an output on the right-hand side. Remember that set evaluates the right-hand side and then assigns the result to the left-hand side. So if we try to use fun, our result will always be 4 plus cos 2. If instead we forget the underscore, you can see that now all of the x's have stopped being green. That means that both this input x and the x's on the right-hand side refer to 2. If we now try to use fun on 7.35, nothing will happen, as we've only defined fun as referring to fun of 2. So don't forget, all of the input symbols should be green. Don't forget the underscore and the colon equals. I'll clear the symbol for now, in case of conflicts later. You have seen options inserted using keyboard shortcuts earlier in this webinar. These options are written with a right arrow called a rule. You will see rules used in a lot of places in the Wolfram language. The general form means that the left-hand side is being transformed into the right-hand side. No variables are being set, but somewhere in the expression, something will get changed based on the left and right-hand sides of the arrow. Here is an example showing the output size of a plot changing. If we change this value here, the output changes size. Don't forget, to see available options, use Command K or Control K. If you look at a piece of Wolfram language code, it is extremely likely that you will see a list, written using curly brackets or braces. They will contain 0 or more elements, separated by commas. Lists are used to represent many different objects, including vectors, regions, iterators, matrices, and sets. Because lists are so common in Mathematica, most of what you do with information and sets of data will be using lists. You will need to know how to quickly and effectively modify them. Here are some examples of functions you may need to use. There are many more on the List Manipulation Guide page in the documentation. Pad right and pad left are for padding lists or arrays to a given length. Rotate right and rotate left cycle the elements a given number of places, and any elements pushed off the end are moved round to the other end. Union and join are ways of joining multiple lists together, the difference being that union does not keep duplicates, so only has one of each element, whereas join just sticks the two lists together. You will often want to only take a section of a list or array. To do this, use the function part. There are many ways to write part. Here is an example on how you use it. First, we will create a one-dimensional list to work with. This range function generates a list of numbers, integers, from 1 to 28, taking every third number. We shall use part to extract elements from that list. In this case, we're taking the third element in list vec. You can also work from the other end of the list, using negative numbers. So here we're taking the last element in list vec. You can use range to take a series of numbers. This is the same as part vec 1, 2, 3, 4 and 5. In part, a range of numbers can be written using two semicolons. The number before the semicolons is the beginning, and the number after them is the end. So here we're doing the same as before. You can take several elements that are not next to each other using a list. Just write a list of the positions of the elements you wish to take. In this case, we're taking the first and the third part of vec. Because part is so commonly used, there is a shorthand. After the list you are taking the part of, type 2 square brackets with the position inside them. Here we are writing vec part 3. You can use all the same functionality as you have just seen. So vec with a list part 1 and 3. Note that when you're using two semicolons to mean range, if you are going from the beginning, you don't need to write 1. If you leave off the first part, it will be assumed that you're going from the start. Similarly, if you write a number at the beginning and nothing at the end, it's assuming that you're going from part 5 all the way to the end of the list. You can see more about this in the guide page, Elements of Lists. If you have nested lists, lists within lists, you will need to use levels to reference parts of it. Levels are also important in expressions in general, but we will use lists to understand how they work. Let's look at an example. Here we're creating an array of letters. Don't worry about the functions used here. It's just so we have some example data to work with. Now, let's use the expression tree form to see the levels in the array. You can see that the top levels are just lists, and the bottom level contains all the elements. The top level is level 0 and is the head of the entire expression. The next level is level 1, and because this is a list of lists, there are just the heads of the inner lists. Then, at level 2, the bottom level, there are the elements. Let's try taking the second column in our array. In an array, each inner list is a row, so to take a column, we will need to access all of the rows at level 1. We can use the word all to do this. To refer to the part of the next level, add a comma and another argument. We then want the second element in all the rows, like this. Say we want to take a group of elements, for example, these two, being the third position of rows 2 and 3. We can't just use all for this, so we have to use a list of elements. So here we have a list 2 and 3, meaning the second and third rows on level 1. Then we want the third part of level 2, so add that as another argument. You can use part with set to change elements in a list or array. Here, we're taking the second row and replacing it with 3 random integers from 1 to 5. Now, if we look at mat again, you can see the original matrix has changed. Another way of holding data is in an association. Lists have sets of things organized by position, whereas an association holds a set of things organized by a label or a key. Here, you can see they are written in rule format. The left-hand side is called the key, and the right-hand side is the value. Around the list of keys and values is an angle bracket and a bar to indicate that it is an association. Note that all the elements, including the keys, will be replaced with their value. So here, I have previously set A to 2, so it is replaced. When you use an association to look up a value by its key, it's like using it as a function, so a single pair of square brackets. You can also look up values by position, exactly the same as a list. Let's take the second value in our association. The result will only be the value, as when you extract data from an association, the keys are transparent. They don't show up. Lists and associations are appropriate for different situations. When working with larger sets of data, it can be a lot quicker to be able to reference an object's name rather than finding its position. Both data types can be of arbitrary dimensions. If the positions of your objects do not change, then a list can be faster, but if things might move, then an association may be necessary. You will often need to get data in and out of Mathematica. When you want to work with external information using the Wolfram language, there are 2 main functions, import and export. There are 172 different formats available for importing into Mathematica. You can see these grouped into data types in the Importing and Exporting guide page. The basic syntax for import is easy. You just use the expression import, and the argument is the full location of the file. If you start typing the file path in quote marks because it must be a string, you should get a pop-up asking if you want to use a file browser. This makes it much more easy to navigate through folders, especially if you don't exactly know the location of the file. As you can see, this could be a very long way to type out the file path, especially if the notebook you are working in is already in the same folder as the data you are importing. Instead, you can navigate through your directories using directory with no arguments. This gives you your current working directory, and set directory. Set directory, with a path inside of it, changes your current working directory. Similar to import, if you start typing a path, a pop-up should appear asking if you want to use a directory browser. To quickly choose the directory where your working notebook is saved, use Notebook Directory with no arguments. if you haven't saved your notebook, this will cause an error. Export is very similar to import. Be careful with import and export formats. The lists are not identical, as in some formats that can be imported cannot be exported, and the other way round. There are very few cases of this, but it is safest to check. When you export, the first argument is the full file path of where the file should be saved. You should include the file's name and extension. The second argument is the thing to be exported. If you want to open a file programmatically, you can use System Open and the file path of the item you want to open. This is the first of a two-part webinar teaching you the basics of the Wolfram language. And this time we looked at a brief introduction to the language, how to use your notebooks more effectively, how to create your own functions and make assignments, and a little about how to deal with lists and data. In the second part, next time, we will look at some visualization functions, how to create interactive applications, and a little of our mathematical and statistical functionality. There are several websites where you can go next if you'd like to find out more. We have many training courses available on demand at wolfram.com/training. If you're already comfortable with code and would like a more fast-paced course, we have a fast introduction for programmers. And finally, we have some message forums where you can ask other users for help. There is the official Wolfram community and a Mathematica Stack Exchange. Thank you very much for listening, and I hope to see you next time.